Hello, friends. Welcome back to ElectriVerse, where we understand electrical engineering in simple language with real plant examples. Today, we are entering part 9 of the VSD series, and this episode is perhaps the most important, most technical, and most eye opening episode of the entire series. Because, friends, in the world of VSD, there's one thing that confuses engineers the most: harmonics. People consider harmonics just a theoretical topic, but in reality, harmonics can heat up transformers, overheat cables, generate current in neutral, and distort the voltage of the entire system. In many plants, drives are running fine, motors are working properly, but still, the transformer becomes unusually hot. Sometimes nuisance tripping occurs, sometimes breakers warm up, sometimes the generator becomes unstable, and engineers think, where is this problem coming from? In this episode today, we will see the true essence of harmonics, in simple language, in full depth, and with real engineering. Today's goal is simple. When you complete this video, you will confidently tell anyone in a meeting what harmonics are, why they occur, and how they are controlled. So, let's get started. ElectriVerse Part 9 of VSD series. Let's go, friends. The very first question: what is harmonics? Let's understand it in the simplest language. Imagine that the voltage of your house should be a perfect sine wave, smooth, clean, and completely round. But when some devices in the system, like VSD, UPS, MPS, LED drivers, become non-linear loads, they do not draw current in a clean sine wave. They draw current in a cut, broken, or uneven manner. Result? The voltage also starts to convert into a broken shape. This distorted wave is what we call harmonics. In simple language, when the shape of the current gets spoiled, that distortion is called harmonics. And when many such distorted currents combine and also distort the system's voltage, that is called voltage harmonics. Just that simple? Friends, remember an important point. Current harmonics and voltage harmonics are not the same thing. Current harmonics mean the load drawing current is not a smooth sine wave. Voltage harmonics mean the grid supply voltage itself has become distorted. Often in plants, the problem is with current harmonics, but the impact is seen in voltage harmonics. A simple example: if a large pump's VSD suddenly draws current in a distorted shape, distortion can also be seen in the secondary voltage of the nearby transformer. That's why the root cause of harmonics is the current, and the victim is mostly the voltage. Now let's go ahead, friends, and deeply understand a very important term: THD, or total harmonic distortion. Think of THD in simple terms as a pollution score. Just as there is pollution in the air, similarly, there is waveform pollution in electricity, and THD indicates how clean your system's waveform is and how much it has been distorted. If THD is low, the system is clean. If THD is high, the system is polluted. Now, THD has two types, and both measure different things. 1. THDI, total harmonic distortion of current. It shows how distorted the shape of the current is. If there are more nonlinear loads like VSD, UPS, rectifiers, then THDI is higher. 2. THDV, total harmonic distortion of voltage. It shows how much the supply voltage itself has become distorted. Voltage. THD usually increases when current harmonics become so high that they also distort the grid's voltage waveform. So, friends, root cause of current harmonics is voltage victim. According to IE 519 standard, how much THD is allowed? To define harmonic limits worldwide, the most trusted guideline is IE 519. This standard clearly states that voltage THD, maximum 5% allowed in most industrial systems. In critical systems, this limit can be more strict. Current THD limits depend on load category: 8%, 12%, 15%, 20%, depending on the short circuit capacity of the system. In simple words, voltage THD must always be kept low. Current THD is allowed a bit more. Because voltage distortion impacts the entire plant, whereas current distortion is mostly handled at the source level. Why is THD important? If THD is high, transformers will heat up, cables will derate, capacitor banks will fail, generators will become unstable, neutral current will increase, sensitive equipment may malfunction. Taking THD lightly is the biggest mistake. What will we see in this episode? In the upcoming scenes, we will examine in detail. Why does THD occur? What is the role of 6-pulse VSD? Why are 5th and 7th harmonics the most dangerous? What impact does THD have on transformers, cables, and generators? How to reduce THD? Line reactors, DC chokes, passive filters, active harmonic filters, multi-pulse drives, active front-end drives. We will understand all of these one by one in depth. Now let's move on, friends. Let's deeply understand a very important truth. Why does VSD generate harmonics? What is its root cause? There's a very simple reason. The rectifier of the VSD does not draw AC current in a smooth, continuous curve. At the front end of the drive, you will find either 6 diodes, diode bridge, or 6 IGBT switches, active rectifier. The working principle of both is similar. The rectifier takes current only from specific portions of the AC wave. We call this selective conduction. Imagine the AC wave coming in a full round shape, but the rectifier only picks the top portions of that wave, ignoring the rest. Result? The current is not a smooth sine wave, but becomes a spiky, uneven, and chopped waveform. When you view this waveform on an oscilloscope, you will notice some parts of the wave are missing. There are sharp spikes in some places, deep notches in others. These spikes plus notches plus chopped sections. Together, we make harmonic currents. And friends, this is not just a theoretical concept. Look at the input current waveform of any real industrial VSD. It is never clean, round, or smooth. As soon as you see the wave, you will immediately understand, yes, the distortion is originating from here. Especially the 6-pulse rectifier is a major source of 5th, 7th, 11th, 13th harmonics. That is why the 6-pulse VSD is considered the primary contributor to harmonic pollution. In the upcoming scenes, we will see why these distortions cause the transformer to heat up, overheat the cables, and why the generator becomes unstable. Why do transformers get hot? Friends, now let's come to a very important practical point. Why do transformers heat up due to harmonics? In many plants, you might have observed the load is only 50 to 60%, yet the transformer's oil temperature rises high. Engineers think the load is low, then why is so much heat coming? Let's understand this in simple language. 1. Harmonics create extra losses inside the transformer. A. Transformer is normally designed for 50 Hz, but harmonic currents bring higher frequency components like 150 Hz, 250 Hz, 350 Hz, etc. The simple meaning of higher frequency, more skin effect in copper, more eddy current loss in the core, more hysteresis loss in the core. These losses are much higher than normal 50 Hz. Understand this. When a 50 Hz transformer encounters the 5th harmonic, 250 Hz, the transformer experiences stress at 5 times the frequency. Transformers are not designed to handle such high frequency losses. 2. The 5th and 7th harmonics are the most dangerous, especially the harmonics that dominate. 5th harmonic, 7th harmonic, 11th, 13th. These harmonics increase eddy current losses multiple times. And this is the reason. The transformer heats up even when the load is normal. 3. What is K factor? The fitness rating of a transformer for harmonics. Special transformers are used for harmonic environments called K factor transformers. K factor in simple language, the harmonic tolerance of the transformer. Example, K1, normal transformer, no harmonics. K4, light harmonics. K13, heavy harmonics. K20, extreme harmonic environment. If your plant has many VSDs installed and you're using a normal transformer, it will overheat even if the load is low. In such cases, K-rated transformers use thick copper improved insulation, and uses low-loss design. 4. Let's look at a real plant example. In one plant, a 1250 kilovolt ampere transformer repeatedly gave high temperature alarms. The load was only 55%. Oil temperature reached up to 75 to 80 degrees Celsius. Investigation revealed that 6 pulse drives, high THD, 5th and 7th harmonics were dominant. The transformer was a normal K1 type. Let's see what solutions were implemented. Line reactors installed, passive harmonic filter added, transformer temperature dropped by 15 to 20 degrees Celsius. This is the real impact of harmonics. 5. Summary: transformers and harmonics. Keep this simple point in mind. When the load is high, the transformer sometimes remains normal. But when harmonics are high, the transformer definitely heats up. Therefore, in VSD-based systems, transformer rating, K-factor, and harmonic mitigation are very critical. Friends, now let's understand another critical point after the transformer. Why do cables overheat with harmonics? Many times it happens that the load is only 40 to 50%, yet the cable feels unusually warm. The insulation color slightly turns brown, and people get confused that the load is normal. Where is the heat coming from? The answer again: harmonics. 1. High-frequency harmonics. Increased skin effect. Under normal conditions, current flows through the entire copper cross-section of the cable. But when harmonics are present, 150 Hz, 3rd harmonic, 250 Hz, 5th harmonic, 350 Hz, 7th harmonic, 550 Hz, 11th harmonic, the current concentrates near the surface of the copper. This is called the skin effect. Higher frequency means a deeper skin effect, which implies the effective cross-section decreases. In simple words, the copper inside the cable is available, but harmonics prevent it from being used. That's why the cable feels thinner, and heat rapidly builds up. 2. Unwanted current flow begins in the neutral, especially in the 3rd harmonic group, 3rd, 9th, 15th, and so on. Triplen current generates in the neutral. This current does not cancel out, but adds up, meaning the current in the neutral conductor can be more than in the phase conductor. You may have heard, the neutral conductor has burnt out. The insulation of the neutral cable has melted. The neutral lug has turned black. All these happen because of triplen harmonics, not overload. 3. Cable derating factor increases. Both IE and IEC clearly recommend that. In a harmonic environment, cables should be derated by at least 20 to 30%. Because with harmonics, R, effective resistance, increases, I squared R losses are higher, sheath temperature rises, insulation ages faster. If derating is ignored, cable life drastically reduces. 4. Heat gets trapped in cable trays and groups. Harmonic-rich current. It does not only produce heat, but also traps heat. You might have said, in the same tray, all healthy cables are normal, but only the drive cable is hot. The reason is clear. VSD cable carries higher frequency current, which totally changes heat transfer behavior. 5. Real plant example. In one plant, a 75 kilowatt motor was running with VSD. The load was only 60%, but the cable surface temperature recorded was up to 80 degrees Celsius. Investigation revealed that THDI equals 42%, 5th and 7th harmonic dominant. Cable derating was not applied. Neutral conductor was undersized. What was the solution? Input line reactor installed, cable derating applied, neutral conductor upgraded, heat reduced by 30 to 35 degrees Celsius without changing the motor load. 6. Summary: cables and harmonics. Always remember these 4 points. Harmonics: increased skin effect. High current flows in the neutral conductor. Cable derating is a must, 20 to 30%. Drive cables trap more heat in the tray. Therefore, in harmonic environments, cable selection, sizing, grouping, and derating are extremely critical. Friends, now let's discuss another important topic. Why do generators become unstable? with harmonics. In many plants, you might have seen that the generator does not overload. The load is only half. The voltage is also normal, yet the generator's speed fluctuates. The frequency jumps, and the automatic voltage regulator keeps adjusting repeatedly. People get confused thinking the load is low. Then why is instability occurring? The simplest reason for this is harmonics. The generator's impedance is much lower compared to the transformer. Low impedance means that harmonic current circulates more inside the generator. This distorts the shape of the voltage. Small jerks are felt on the torque, and the magnetic field of the generator becomes unstable. These jerks disturb the generator both mechanically and electrically. The second problem is with the automatic voltage regulator and governor. Both controllers expect a smooth sine wave. When a harmonic wave occurs, the automatic voltage regulator receives an incorrect voltage sample and the governor receives an incorrect frequency sample. The result is automatic voltage regulator overreaction, voltage fluctuations, governor's hunting movement, and the generator's speed does not run smoothly. Another thing to understand is the fifth harmonic is the most dangerous for the generator. The fifth harmonic rotates in the opposite direction of the flux, causing torque fluctuations, humming sounds, and rotor vibrations. Often, the humming you hear in a generator is not due to load, but due to the fifth harmonic. For harmonic loads, the generator rating must always be derated. According to many guidelines, the generator may need to be derated by 20 to 50% for harmonic loads. If derating is ignored, instability is guaranteed. Understand a real example. A 800 kVA generator was only half loaded. Still, the frequency was changing repeatedly. Voltage flickering was occurring and the generator was hunting. Upon checking, high current distortion was found. The fifth harmonic was dominant and the input line reactor was not used. As soon as the line reactor was installed, the system calmed down. The generator started running cooler. The frequency stabilized and the humming almost disappeared. Remember a simple rule. Generator and VSD are only safe together when harmonic mitigation is proper. Friends, now let's understand another very critical topic. Why do capacitor banks fail along with harmonics? You might have seen in plants that capacitor banks suddenly explode, fuses melt, can lights turn brown, or capacitors bulge. The first blame is usually on the power factor controller. But the real problem lies in harmonics. First reason, capacitors do not like high frequency at all. Capacitors are only designed for normal frequency, such as 50 Hz. But when harmonics are generated, the current inside the capacitor increases very rapidly. Higher frequency means higher current. Higher current means extra heating. This overheating creates hotspots inside the capacitor. And after some time, the capacitor fails. Second reason, resonance. Capacitor and system inductance together form a resonant circuit. Think of it in simple language. A capacitor stores energy, an inductor stores energy. When both match at a particular harmonic, the system vibrates like a drum. This vibration means the current becomes very high. This very resonance gives the capacitor banks the most dangerous shock. Often capacitor blasts are not caused by overload, but by resonance. The third reason is that the power factor controller gets confused. The power factor controller measures the angle between voltage and current. But in a harmonic waveform, the angle is not measured correctly. The controller thinks the power factor is low and it switches on the capacitor stages. This capacitor stage turns on at the wrong time when the voltage is distorted. This causes the capacitor to draw even more current and it fails after some time. The fourth reason is that capacitor banks are installed without harmonic filters. Normal capacitor banks are not safe for harmonic loads at all. In such plants, it is necessary to install the harmonic filter capacitor bank in series so that the capacitor only handles the main frequency and the harmonics are diverted to the filter. If only a plain capacitor bank is installed, it begins to absorb harmonic currents, leading to overload. A real plant example. In a cement plant, A 400 kilovolt ampere reactive capacitor bank was failing every 12 days. The capacitor would bulge, the fuse would melt, and people would smell burning as soon as they opened the panel. Investigation revealed that the plant had a significant number of drives, with the 5th and 7th harmonics being dominant, and the capacitor bank was of plain type. A series reactor was installed, and thereafter, no failures occurred in 6 months. Summary: the failure of a capacitor bank is less due to overload and more due to harmonics. Important points to remember. 1. Capacitors are not suitable for higher frequency currents. 2. Resonance capacitor can explode. 3. Power factor controller takes incorrect decisions in distorted waveforms. 4. Installing capacitor banks without harmonic filters is risky in harmonic-rich plants. Therefore, capacitor banks should not be directly connected with VSD loads unless the filter is in series. Friends, now we understand a very practical and very powerful solution. This solution is used in almost every VSD system, and its name is line reactor and DC choke. Many people consider the reactor just a coil, but in reality, the reactor is a silent bodyguard of the VSD system. It controls harmonics, smooths the current, and increases the lifespan of both the transformer and the cable. Let's understand this in simple and deep language. First point. The line reactor rounds off the spikes in input current. The rectifier of the VSD draws current in small spikes. These spikes create harmonics in the system. The line reactor is a magnetic coil that softens these spikes in current. Think of it with a simple example. Just as we smooth a rough surface with sandpaper, the line reactor smooths the waveform of the current. When spikes are smoothened, harmonics naturally decrease. Second point. The line reactor allows the transformer to operate within the comfort zone. The transformer heats up due to harmonics because high frequency losses increase. However, where the line reactor is used, the transformer does not receive distorted current. It receives filtered, smooth current. This significantly reduces the transformer's temperature. In many plants, after installing a line reactor, the oil temperature drops by 10 to 20 degrees. Third point. The line reactor absorbs surges and transients. Small surges can occur in the grid at any time. Sensitive components of the VSD, such as the rectifier and DC bus, cannot handle these surges. The line reactor acts as a shield. As soon as a surge occurs, the reactor absorbs it, and the disturbance does not reach inside the VSD. Now, let's understand the DC choke. The DC choke is installed inside the VSD, whose function is to smooth the DC bus current. When the DC bus is smooth, the current on the inverter side is also smooth, and when both input and output are smooth, harmonics reduce dramatically. With the DC choke, the drive's lifespan increases, motor heating decreases, and VSD trips are significantly reduced. Real plant example. In a plastic industry with a 100 kilowatt VSD, all the drives were tripping overcurrent every 6 to 7 days. The transformer was also showing unusual heat. Line reactor and DC choke were installed. The difference was visible within a week. The drive started running smoothly. Transformer temperature decreased, current waveform became clean, and trips almost stopped. This is the true power of the reactor and choke. Summary: remember 3 simple lines. 1. Line reactor smooths the input current. 2. Line reactor protects the transformer, cable, and VSD. 3. DC choke stabilizes the DC bus and significantly reduces harmonics. If the harmonics are high in the VSD plant or the transformer shows unusual heat, the very first step is to install a line reactor or DC choke. This is a simple device, but it provides a very significant stability improvement in the plant.
Friends, Meta, SEX 0.5. Now let's understand a very powerful solution that directly removes harmonics from the system. Its name is passive harmonic filter. Many people think a filter is just a capacitor and reactor, but in reality, a passive filter is a carefully tuned circuit that pulls harmonic currents towards itself and makes the system clean. Let's understand step by step how a passive harmonic filter works. SEX 0.5. First point, passive filter only absorbs harmonics. It does not affect the main frequency. This filter acts as a side lane where harmonic currents are redirected so that the main cable, transformer, and generator receive clean current. Understand this with a simple example. Just as heavy traffic on the road is diverted to a bypass road, similarly, a passive filter diverts harmful harmonic currents. The second point is that a passive filter is tuned for a specific harmonic. Often in drives, the fifth and सातवां हार्मोनिक डोमिनेट होते हैं. #X 0.5. पैसिव फिल्टर्स इन्हीं स्पेसिफिक फ्रीक्वेंसीज पर ट्यून किए जाते हैं. जब सिस्टम में वो हार्मोनिक अपीयर होता है, तो फिल्टर उस करंट को अपने अंदर पुल कर लेता है. इससे ट्रांसफार्मर, केबल्स, मोटर एंड VSD हार्मोनिक करंट से फ्री हो जाते हैं. तीसरा पॉइंट, पैसिव फिल्टर सिस्टम को रेजोनेंस से प्रोटेक्ट करता है. जहां कैपेसिटर बैंक डायरेक्टली कनेक्ट होता है, वहां रेजोनेंस का रिस्क होता है. लेकिन पैसिव फिल्टर में रिएक्टर सीरीज में लगा होता है, जो कैपेसिटर को प्रोटेक्ट करता है और रेजोनेंस को खत्म करता है. इसलिए पैसिव फिल्टर पावर फैक्टर इंप्रूव भी करता है और हार्मोनिक्स रिड्यूस भी करता है, बिल्कुल सेफ तरीके से. चौथा पॉइंट, पैसिव फिल्टर लो कॉस्ट और लो मेंटेनेंस सॉल्यूशन होता है. एक्टिव फिल्टर के कंपैरिजन में पैसिव फिल्टर इलेक्ट्रिसिटी नहीं कंज्यूम करता. इसका मेंटेनेंस ऑलमोस्ट जीरो होता है. इट वर्क्स साइलेंटली एंड कंटिन्यूअसली इंप्रूव्स द सिस्टम्स हेल्थ. Sex 0.5. Real plant example. Multiple drives were installed in a food processing plant. Transformer overheating, cable heating, and capacitor bank failure had become regular issues. Sex 0.5. A passive filter was installed, tuned specifically to the fifth harmonic. Within a week, the transformer temperature decreased by 10 degrees. Capacitor failures stopped completely, and drive trips ceased. The plant team reported that they had never seen such clean power quality before. Sex 0.5. Friends, now we are going to understand the most intelligent solution for harmonics. Its name is active harmonic filter. This filter is not a normal coil or capacitor. It is a smart electronic device that monitors the system in real time and injects current against harmonics to clean the entire system. Let's understand it step by step in detail. The first point is that the active filter measures harmonics in real time. The active filter system continuously scans the current. The harmonic with a high value is immediately identified by the filter. This cannot be done by a passive filter because a passive filter only targets a fixed harmonic. The active filter is like an intelligent brain that changes its decision every second in the system. Another point is that the active filter injects opposite current. Just as noise-cancelling headphones generate reverse sound waves to cancel noise, similarly, the active filter generates reverse harmonic. The current injects and brings the original harmonic close to zero. Understand this in simple language. If an unwanted wave is rising in the system, the active filter generates a wave downward. Both waves meet and the harmonic cancels out. The third point, the active filter works on multiple harmonics. Passive filters target only the fifth or seventh harmonic. But the active filter can target the fifth, seventh, ninth, 11th, and almost every harmonic. It cleans the entire system, not just one harmonic. That's why, in a mixed harmonic environment, the active filter is the most powerful solution. The fourth point, the active filter also reduces neutral current. The reason for triple harmonics is unwanted current flow in the neutral conductor. The active filter injects opposite current into the neutral, almost eliminating the overload of the neutral conductor. In industry, the neutral conductor burning is a major issue. Reasons for triplen are active filters. The active filter completely solves the issue. SEX 0.5. Fifth point. Active filter generator systems are very effective. Generators cannot tolerate harmonics. However, the active filter provides smooth, clean current supply to the generator. This stops generator hunting, reduces humming sound, and stabilizes both voltage and frequency. After installing the active filter in Kai plants, the generator's efficiency visibly improves. Let's look at a real plant example. Multiple drives were installed in a fertilizer plant. The generator was repeatedly becoming unstable, the capacitor bank was failing, and the transformer was overheating more than normal. An active harmonic filter was installed to solve this problem. In just 1 week, the generator stabilized, the neutral current halved, process flicker disappeared, and the transformer oil temperature noticeably decreased. The plant reported in writing that after the filter, the power quality felt clean for the first time. Summary. Remember these 3 things always. 1. एक्टिव फिल्टर इंटेलिजेंट डिवाइस होता है जो रियल टाइम में हार्मोनिक्स को मेजर करता है. 6. ये ऑपोजिट करंट इंजेक्ट करता है जिससे हार्मोनिक्स कैंसिल हो जाते हैं. 3. ये 5वां से लेकर 11वां तक मल्टीपल हार्मोनिक्स को कंट्रोल कर सकता है और सिस्टम को ऑलमोस्ट प्योर क्लीन कंडीशन में ला सकता है. अगर प्लांट में मिक्स्ड हार्मोनिक एनवायरनमेंट हो या जनरेटर अनस्टेबल हो या कैपेसिटर बैंक्स फेल हो रहे हो तो एक्टिव हार्मोनिक फिल्टर सबसे बेस्ट सॉल्यूशन होता है. फ्रेंड्स, नाउ वी अंडरस्टैंड अ वेरी एडवांस्ड हार्मोनिक सॉल्यूशन. इट्स नेम इज multi-pulse drive. This solution is used in the industry when the load is heavy, the transformer is critical, and the power quality standards are very strict. Let's understand in simple language how the multi-pulse drive reduces harmonics. First point. A 6-pulse is a normal VSD. A multi-pulse drive is its upgraded version. In the rectifier of a normal drive, there are 6 switches. That's why it is called a 6-pulse drive. This 6-pulse drive generates harmonics, especially the 5th and 7th harmonics. The multi-pulse drive solves this issue at the design level. Second point. The multi-pulse drive has 2 or 3 rectifier systems. When we use 2 rectifiers, it is called a 12-pulse drive. And when we use 3 rectifiers, it is called an 18-pulse drive. These rectifiers are operated at different angles. Their generated harmonics cancel each other out. This cancellation is achieved during the design phase. Third point. A special transformer is used with the multi-pulse drive. It is called a phase-shifting transformer. The secondary winding of this transformer is shifted at specific angles, such as 30 degrees or 20 degrees. This shift naturally cancels harmonics without the need for any extra filters. Let me explain this with a simple example. Just as 2 people exert force in opposite directions, causing the force to cancel out. Similarly, in a multi-pulse drive, harmonic currents are generated in opposite directions and cancel each other out. Fourth point. A multi-pulse drive is generally better than passive or active filters. Harmonics are cancelled within the source itself before any distortion enters the system. Therefore, the multi-pulse drive is considered the cleanest technology for power quality. In many refineries, petrochemical plants, and critical process facilities, multi-pulse drives are the first choice, especially where drive ratings are very high, such as 500 kilowatts, 700 kilowatts, or 1 megawatt class motors. Fifth point. For generator systems, multi-pulse drives are quite stable. They tend to become unstable with generator harmonics. However, multi-pulse drives supply clean current to the generator. This keeps the frequency stable, voltage stable, and hunting almost zero. Therefore, in generator-based plants, multi-pulse drives are the best choice. Real plant example. In a refinery, 400 kilowatt VSD loads were initially 6 pulse. Transformer overload, voltage flicker, and capacitor bank failure were regular issues. A 12 pulse drive was installed. Within just 1 month, the transformer temperature reduced, power quality improved, and flicker was completely eliminated. The plant documented this in writing. After the power quality multipulse drive, it became completely clean. Summary. Remember 3 things. 1. Multipulse drive cancels harmonics at the design level. 2. Phase shifting transformer naturally eliminates harmonics. 3. For large VSD loads, multipulse drive is the cleanest and most reliable solution. This technology is expensive, but in critical plants, this investment makes the system safe and stable. Friends, now we come to the most advanced solution in harmonics. Its name is Active Front-End Drive, also called AFE drive for short. AFE drive is the next level of VSD technology. It is not a normal 6-pulse or 12-pulse system. It is a smart and fully controlled rectifier system that makes the input power perfectly clean and reduces harmonics to near zero. Let's understand in simple language what the actual function of AFE drive is. First point. AFE drive does not use diodes on the input side. Normal VSDs have 6 diodes that draw current in small spikes. This causes harmonics to generate. But AFE drive uses insulated gate transistors instead of diodes. These transistors draw current smoothly, roundly, and in a controlled manner. The result is clean input current and almost no harmonic distortion. Understand this with a simple example. A normal diode rectifier is like a rough driver. An AFE is like an experienced driver who drives the vehicle smoothly and does not create disturbance in the system. Second point. AFE drive controls power bidirectionally. This technology can not only take power inside the drive, but also push power back into the grid. This is called regenerative braking. Where there are cranes, elevators, downhill conveyors, or any lifting application, AFE regenerative braking can send energy back to the grid and keep the system completely cool. It also eliminates the need for braking resistors and significantly reduces heat generation. Third point. AFE drive is an expert in voltage balancing. Many plants face voltage unbalance. Normal rectifiers struggle with unbalance and current distortion increases. But AFE drive actively corrects the input voltage. It provides a stable and healthy voltage supply to the motor. This reduces the motor's heating and extends the system's lifespan. Fourth point. AFE drive systems are perfect for generator applications. Generators become unstable with harmonics, but AFE drive draws current like a pure sine wave. The result is zero hunting, zero flicker, smooth voltage, and stable frequency. For generators, AFE drive is the safest VSD technology. Fifth point, AFE drive easily passes the power quality standards. Industrial standards like energy quality guidelines have strict limits on harmonic currents. AFE drive draws almost clean current, so it automatically passes these standards and does not require additional filters. Real plant example. In a pharmaceutical industry, multiple mixers and centrifuge drives operate on AFE technology. Initially, harmonics were high. The generator was unstable, and voltage flicker was a common issue. As soon as the AFE drive is installed, the system becomes completely silent. The generator becomes stable. Voltage flicker reduces to zero. And the operator actually said that the system is now running butter smooth. Summary. Remember three simple points. 1. The AFE drive draws current smoothly and controlled on the input side and brings harmonics close to zero. 2. It allows bidirectional power flow which sends regenerative energy back to the grid. 3. In generator-based plants, critical process plants, and strict power quality plants, the AFE drive is the most advanced and safest choice. AFE is a slightly expensive technology, but where stability and power quality are priorities, it is a perfect long-term solution. Friends, now we discuss a topic that people generally ignore. The topic is the spread of harmonics, or how harmonics travel throughout the plant. Many engineers think that harmonics are only around the VSD panel or only in the motor cable. But the reality is different. Harmonics are generated in one place, but their effect is visible across the entire electrical network. Let's understand step by step. First point. Harmonics also travel upstream. If a motor has a VSD installed and it is producing harmonics, then these harmonics are not only in the motor's cable. They exit the cable, enter the panel, then go to the MCC and reach the transformer. That's why drives installed in one corner of the plant can disturb equipment in another zone. We call this backward propagation. Second point. Harmonics also disturb downstream equipment. If the plant has UPS systems, PLC power supplies, sensitive analyzers, digital sensors, and communication modules are installed, then harmonics directly disturb them. This causes communication errors, PLC resets, sensor malfunctions, and UPS overheating issues. Often in the plant, a single sensor failure stops the entire process, and the root cause is harmonics, which no engineer has noticed. Third point. Harmonics distort the shape of voltage. Under normal conditions, the voltage wave is smooth. But with harmonics, the shape of the voltage wave becomes rough. This rough shape puts extra stress on motor insulation. The result is overheating of motor windings, early aging of insulation, and unexpected winding failure. Many motors fail prematurely for this reason. Fourth point. Harmonics give incorrect readings to metering systems. You may have often seen that the power meter readings are unstable, and in some panels, The load counts jump. In the current transformer, heating generates heat. All these issues are caused by harmonic distortion. Sometimes, penalties can also be imposed because the power factor is misread. Fifth point, harmonics. Overall drop the power quality. When harmonics spread throughout the network, problems appear at a certain point, but the actual cause is elsewhere. The transformer heats up, but the root cause is the drive. The UPS trips, but the root cause is the motor starter. The capacitor bank fails, but the root cause is phase angle distortion. That is why harmonics are not considered just a local problem. They are a health issue for the entire plant. Real plant example. In a large food plant, only 3 drives were installed. Still, voltage flicker was occurring across the MCC. The digital water meter was giving incorrect readings, and the fuses of the capacitor bank were melting daily. Investigation revealed that harmonics were traveling both backward and forward. A line reactor and passive filter were installed, and the entire plant became stable. Summary. Always remember 3 points. 1. Harmonics are generated in one place but travel throughout the plant. 2. Sensitive equipment behaves incorrectly with harmonics. 3. If harmonics are not controlled in the plant, power quality drops and reliability decreases. Therefore, harmonic control is not just an issue of the drive, it is a health check of the entire plant. Friends, now we come to the most practical scene of Part 9. This scene provides you with a complete step-by-step strategy on how to control harmonics in any plant. Many plants face the problem that engineers know that harmonics are high, but they do not understand what should be the starting point and in what sequence the solution should be applied. Today, we will understand this entire roadmap in simple language. First step, identify the nature of the load. First, understand how many drives are installed in the plant, what are their kilowatt ratings, and which loads operate continuously. Where centrifugal pumps and fans are present, drives run continuously, and most of the harmonic share comes from here. Where conveyors or crushers are present, the rectifier behavior is different and the distortion pattern varies. Understanding the nature of the load is the first step. Second step, measure harmonics in the system. Many plants make guesses. Harmonics will be high. Decisions are not made based on guesses. You need to measure current distortion and voltage distortion with an actual harmonic analyzer. This measurement reveals how high the harmonics are and which order of harmonics is dominating. The third step is to perform a health check on the transformer and generator. The direct impact of harmonics is seen in transformer heating and generator instability. It is important to check the transformer oil temperature, the generator's hunting pattern, and the cable temperature. If the transformer is unusually warm, it is a strong indicator of harmonics. The fourth step is to apply mitigation step by step, starting from basic measures. First, install a line reactor. The line reactor smooths the input current and harmonics naturally decrease. Then, install a DC choke. This stabilizes the DC bus and reduces rectifier distortion. If only the fifth and seventh harmonics are high in the plant, use passive harmonic filters. If mixed harmonics are high, then active harmonic filters are the most powerful solution. If drives have large ratings or power quality is strict, then use multi-pulse drives. If the plant is critical or has generator-based supply, then active front-end drives are the best long-term solution. The solution is always chosen according to the size of the problem. Fifth step, After harmonic solutions, re-evaluate the system. After installing mitigation, remeasurement is important. Sometimes, immediately after installing line reactors, harmonics reduce dramatically and further filtering is not needed. Sometimes, filters need to be tuned to clean the harmonics. System re-evaluation always provides final confirmation that power quality is stable and equipment is operating within safe zones. Real plant example. In a box manufacturing plant, multiple drives were installed. The transformer was overheating. The UPS reset was done, and digital sensors gave incorrect readings. A step-by-step strategy was followed. A line reactor was installed. A DC choke was installed. A passive filter was tuned. And finally, an active filter was used. In 3 weeks, the system became clean, and the plant reported that power quality is now completely stable. Summary. Remember the entire roadmap in 3 lines. 1. First, understand the load and measure harmonics. 2. Start mitigation with a line reactor and select the filter or drive technology according to the problem size. 3. Final measurement always confirms that the system has been cleaned. Following this sequence, any plant can be safe from harmonics. Friends, this was part 9 of the VSD series. Today, we understood the complete truth about harmonics. What is its origin? How it affects the plant? And how we can keep the system clean and stable. If you have watched this video up to this point, it means that you truly want to understand engineering deeply. ElectriVerse's goal is also to give you that clarity, which will take your career to the next level. If you found this video valuable, please like it, share it in your plant's WhatsApp groups, and subscribe to the channel so you don't miss the next part. You have been watching ElectriVerse, where every spark tells a story. Stay charged, stay safe, stay happy.